All right. So a couple of things off the top. You'll see up on Canvas, there's this final Learn Smart assignment that I'm going to have you do before Wednesday. We're going to start linear regression on Wednesday, so I want to kind of have you prime a little bit. This should just take 10, 15 minutes, kind of go through, kind of just so you're a little bit more familiar with some of the things I'm talking about. Not a perfect understanding by any means. I'm also going to push the due date on that Excel assignment to be next Monday at the end of the day, the same as the Connect assignment. So you have a couple extra days there. We should have worked through everything you'll need after today. And even before that, you could have made a pretty good chunk of the way through it. But just kind of giving you a little bit extra time there. I know I'm giving you this extra Learn Smart this week, so I wanted to kind of make sure I gave you enough time to complete that Excel and Connect assignment. Okay. Other than that, I think we should be good on kind of just housekeeping stuff. But are there any questions from you before we kind of jump into the material today? Another thing I wanted to mention is I don't know at what point, but sometime this afternoon, I'll get up some practice exams on Canvas as well for the final. So you'll have those as we start getting closer to that date. Other than that, we'll kind of pick up where we left off on that two population hypothesis testing or two population HT blank file. I've got it just saved from the work that we've been doing. That's why mine kind of looks a little bit different. But if you've been working along, we left off on this male data worksheet where we had a two population example. We had two sample means, but we only had sample variances. Okay? So we calculated the test statistic already and we had found the p-value. But we could also have done the critical value approach. So I'll kind of walk through the p-value and critical value approaches here, how we find those critical values in Excel. So go back and remember what we had was we were looking at a two-tailed test, right? So I think the other example when we had proportions of a left-tailed test for you. Here we did a two-tailed test. So when I'm thinking about critical values for a two-tailed test, where I've got is that true difference either equal to 0, oops, and the alternative would be that that true difference is not equal to 0. I'm wanting to find the critical values now. Remember, I have a pair of critical values of the two-tailed test, such that alpha is now not just in one tail, but alpha is the total area in the tail. So that means I have half of alpha on each side. So when I know the area in the tail, and I want to find the corresponding kind of t-value or critical value in this case, remember critical values can be standard normal or student t-values. It just depends on what distribution we're using. We can use that t dot inv function, tell it the area that we want in the tail, and it will return to us what that t-value is. Now, it always uses the area in the left tail. So when I tell it alpha over 2, it's actually going to give me that negative value. So we can see here if I go in and use that t dot inv, I've got my area I want in the tail is alpha divided by 2, comma, what's my degrees of freedom? Well, that was where we had that nasty equation, but I already had it entered into Excel, so you're not going to have to type that in. So there's my degrees of freedom. Let's see if I can scroll just a little bit. So there we go. So that should give me this negative critical value because it's always using the area in the left tail. So when I'm telling it alpha over 2, it's looking at the area in the left tail. So I hit enter. Sure enough, I get the value, but it's negative. Well, that's okay because that is one of my critical values. It's just the other critical value I have is that same value, but positive. So I can just right next to it put the absolute value of that. And now I've got my pair of critical values right there. Okay. So with a two-tailed test, you have to indicate somehow, and this is a good way to do it in Excel, is here I've got two critical values. One's positive, one's negative, but they're the same value. Okay. Any questions on that before we keep moving here? So if I want to find my critical value at these other confidence levels, right? What's the problem going to be if I just copy this down? So I want it to keep updating alpha, but that degrees of freedom, well, that's always in the same cell. So I'm actually going to need to freeze that cell reference. Right? Now, when I copy it down, it's using the same degrees of freedom, right? Same student t-distribution. It's just looking up different t-values for different areas in the tail there, or different alpha values. Okay? So now, if I copy these down, I'll get my pair of critical values at each one of these different confidence levels. Okay. Any questions here before we keep moving? Okay. So last class, we had found this p-value. If I wanted to make my rejection decision using the p-value approach, we said we're always going to do, is the p-value less than alpha? If it is, we reject. If not, we fail to reject. So a nice, easy way we said we could do this in Excel is using that if statement. Right? If my p-value, this is over here, is less than alpha, comma, if that's true, put the word reject. So we had to put that in quotation marks. If comma, if that's not true, put the word fail to reject. Let me go over so this is all in one line for us here. Okay. So that's basically just checking to see, is the p-value less than alpha? If it is, I can reject. If it's not, I fail to reject. Now, if I copy this down, if I want to make my rejection decision at different confidence levels, I'm still using the same sample evidence. I still have that same p-value. It's just I'm comparing it to different threshold alphas. So I want my alphas to update when I copy this down, but this p-value should always be the same, right? So I'm going to go here and freeze that cell reference. Okay. Now, when I copy this down, I'm always using the same p-value. I'm just comparing to different threshold alphas. Okay. So if I copy this down, I'll see here, okay, well, it makes sense, right? This p-value is less than 0.1 and 0.05, but not quite less than 0.01. So it automatically makes that rejection decision pretty quickly for me, right? Or kind of automates it. Any questions before we move on to the next thing? Want to see a cell again, or what did I do here? So the other rejection decision we kind of approach is that critical value, right? We had our rejection region. And we said, if the test statistic's anywhere in this rejection region, we can reject. So the mathematical kind of representation of that is the absolute value of my critical value less than the absolute value of my test statistic? If it is, I reject. If it's not, I fail to reject. So I can do that in Excel as well, right? Using this if statement, I can say if the absolute value of this critical value is less than the absolute value of my test statistic, which was way over here, comma, that holds, then I should be rejecting. If that doesn't hold, comma, then I fail to reject. I can't quite get this all in one line here, so I guess if I just said fail here, maybe it makes it a little bit easier, but fail to reject. Now, once again, when I copy this down, I'm always using the same test statistic. I'm just comparing it to different threshold t-values or different threshold critical values. So I want this critical value to update, but my cell reference for the test statistic, right? I'm always using the same test statistic when I'm making that rejection decision. Right? I found the same sample evidence. I'm just saying, is this sample evidence enough to reject at different levels of confidence, right? Or different alpha values. Okay. So now if I hit enter there and copy this down, I should get the exact same rejection decisions. Okay. Kind of see this all in one line here. Any questions there before we keep going? And so this will all be in that completed version that's already up on Canvas, but all the work we do in class, I'll save this file after today and I'll kind of upload that one. So you'll kind of have both. I did a couple, threw a couple extra things in here that weren't in that original completed file. So, and it also matches exactly what we did in class. So if you were here, probably makes more sense to look at this one just because it's exactly how you would have been following along. Okay. So we've got our rejection decisions, right? All is well. So, there's a decent amount of work there. We had this test statistic we had to calculate, right? Using Excel to be our calculator, finding the p-value, critical values, making the rejection decision using the if statement, I can actually find that p-value in a much easier way, right? So to find that test statistic, I had to find the mean, the variance, and the sample size for both these groups, males and female BMI. Right? There's a built-in shortcut in Excel, and we'll kind of show its strengths and weaknesses here today. So what you do is you don't even calculate the sample means yourself. You just say, look, here's my first group, right? So my first group was males, right? I was looking at that male BMI variable. So I'm just going to select the variable that I would have calculated the sample mean, variance, and sample size of, comma. You can kind of see in the formula bar here, it's got a comma. So I could keep going here, but I want you to be able to see it. So I'll scroll up to the top for us so we can see what it looks like. Once I selected that, it puts that cell reference in there. The second array, so I had a comma, is on that female worksheet. And I was showing the other class, so I'll scroll up here. So I'm just going to select this female BMI variable. Control Shift or Command Shift on a Mac. Notice it puts that female worksheet reference up there for me. I'm going to go back, actually here. I don't want to do that. Let me show you again, because I just kind of cheated using the shortcut. So I selected that female BMI variable. And I can see my formula bar up here. Before I go back to my sheet, I'm going to just put that comma in there, right? So here was my first variable, was that male BMI. I had to go to the female sheet to get my second variable, which was female BMI. We go back to my male data sheet. Now notice when I click on the sheets, it automatically puts that reference in there for me. But once I'm on the male worksheet, I don't really need that in there. I could leave it in there, but I'm just going to get rid of it to make it a little more simple because I don't have to reference the worksheet that I'm on, right? So now, after that second comma, I need to tell it how many tails is this test that I'm doing. Well, we had a two-tailed test here, right? So I'm going to put a 2. It's either a one-tailed test or a two-tailed test. Here we have a 2, comma. Now we're only going to have 2 types of examples that we're looking at in this class. So the first one is this one where we have 2 sample means and they don't have the same sample variance. So notice here, type 3 is 2 sample means, not the same unequal variances, right? So we're going to put it to type 3 T-dot test, right? That basically just tells Excel, I've got 2 sample means. I want you to do this hypothesis test where you find the difference between the 2, turn it into a test statistic, look that up in the table. It's a two-tailed test, so find the area that's more extreme than that test statistic and multiply it by 2 to give me my p-value. So this T-dot test does all the work behind the scenes, calculates the sample means, variances, sample sizes, calculates the test statistic, all behind the scenes, and then spits back out at you the p-value. It's kind of what we call a black box. It does all this stuff that you can't see behind the scenes. Now, the only other type of example that we're going to look at, and we'll do that by the end of the class today, is going to be this paired example, or what we call matched pairs. Right? That's not this example, but that's the only other one we'll use in this class. So when I see that Excel assignment, inevitably someone will put a type 2 in here. We're not doing those. It'll never be 2 for this class. I'm telling you right now, right? We're only going to be dealing with examples like this one where it's a 2 sample mean unequal variance or a matched pair. This one where we have 2 sample means in the same variance, not going to waste time talking. There are cases where that's relevant, but more often than not, we're not. I mean, to have 2 samples of the exact same variance isn't very likely, right? So the idea there is actually that you're taking 2 samples from the same population, so you know that the variances are the same. That just often, I mean, it's just not a very relevant example for we'll have no examples like that, right? It's not very, very common. So we're only going to have these one or either a 1 or 3 here. Here we've got the 3, the 2 means unequal variances. So if I hit enter here, I should get the exact same thing I found up here. Sure enough, I do, right? It's a little different because I think this one's rounded to a different decimal. I can change the formatting here. Right, we can go out a little bit further. So we can go out a little bit further with this one. Now you'll notice it is off at a certain decimal. So this T-dot test, because it does all this work behind the scenes, it does have to round things out at some decimal. So you're going to be a little off here, but I mean, we're only off out to the what, 8th decimal or something like that. So it's not perfect, but off of the 8th decimal, we're getting pretty precise still with it and saving ourselves a lot of work, right? We can go through and do the steps if we actually want to make the exact calculation. But at least if we're looking at data to get a first kind of idea, that T-dot test is a real nice way to do it very quickly. Okay. Any questions on that? So you select your 2 columns of data that you would have been finding the sample means for. It does all the work for you. Tell it the type of tails 1 or 2. And then here we had a type 3. And the next example that we'll start talking through here in just a second would be a type 1, which is matched pairs. That's not what we had here. Okay. Now, once I have this p-value, I can make my rejection decision using it the exact same way I did before. Okay. Any questions there? So I just want to point something out at here before we jump into matched pairs. We were using, oh, here it is, this assumed true difference of 0, right? I said that's what I'm always going to give you guys. It's pretty common that is the assumed true difference because, you want to know, do these 2 groups have a different mean? Is one mean greater than the other? Is one mean less than the other? But maybe here I said, well, okay, maybe I could say that male BMI is, I guess, different than female BMI, right? But can I say, is it different by a factor of like 0.1, right? Is that difference something other than 0.1, or is it a bigger gap in between these 2? So I want to choose a different hypothesized true value. Here I might assume that the true difference is 0.1 instead of 0. So if I do 0.1, notice my test statistic, my p-values update. If I kind of did it step by step and I calculated these sample means on their own, but that shortcut, that t-dot test doesn't change at all. And that's because that t-dot test can only use the assumed true difference of 0. So I didn't show you how to do it step by step for no reason, right? Often you don't have to do it that way because that assumed true difference is 0. But if you ever had a situation where you want to know, well, is that difference greater than a certain amount or less than, or is that gap just, bigger than a certain size? I can't do that with the shortcut t-dot test, right? I mean, I could play around with this. It's just never, it's not going to change, right? But if I am using that assumed true difference of 0, it will give me the exact, well, I say the exact same value. It's going to be off at like that 8th or 9th decimal, but it's going to be a very, very, very good approximation. Okay. All right, so pros, saves us a lot of work. If the assumed true difference of 0, cons, we can't do a hypothesis test here for a value other than 0 using that t-dot test. So to compare to what we just did, the example we were just working through, we had 2 groups and we were looking at the difference in the sample means, but we also thought about, like, there was situations where we had 2 different time periods, right? And we took the difference in the average across those 2 time periods. So matched pairs is going to be kind of similar to that, but a little bit different. So we're going to end up with a before and after time period. And it doesn't have to be time, but the majority of the examples I'll give you will be time. In fact, I think all the examples other than the one I'm going to show you in Excel will be time, but the one in Excel I think is kind of interesting. And also I wanted to point out that you don't have to have before and after. You can match other things as well. And what we're matching on is the fact that we have the same sample. So the example that I have here is, like, let's say I have a manager and they change this workstation layout and they want to know, does it change productivity, right? Maybe are people moving around this production process or something better than before? And so I've got the same 10 workers, right? So my population, I don't have 2 populations. I don't have 2 samples, right? I've got the same 10 workers. I just have a before and an after measure of their productivity. So what we're going to do is think about, we've got 10 workers. So I don't know. You think about, I've got all these different employees. I don't know, John, Joe, Janice, I don't know, a bunch of J's. So I've got their before and I have their after productivity measures. So maybe this is something like 8 and 10, 14 and 18, 9 and 7, etc. Right? So instead of finding the average productivity before and the average after, and then looking at the difference there, well, I don't have to take the difference in sample means because I've got the same 10 people. So what I'm going to do is find, well, what was the difference or what was the change in productivity for each person? So this person, productivity went up by 2. This person went up by 4. This person went down by 2. I would have the change in productivity or that difference in productivity for every single person. Now what I'm going to do is find the average change in productivity. Because it's the same kind of 10 people, it's almost like I'm controlling for who the productivity change was for, right? I don't have, like with the female male BMI, that was two completely different samples. There was nobody that was in both of those samples, so I couldn't match them on anything. Here, it's the same 10 people, so I can match these productivity measures off of the employee. Right? So I'm going to find the mean of this difference variable, and we're going to call that the mean difference. It's going to look very similar to what we were doing when we had one population sample mean examples. I'm then going to find the variance on that difference variable. It's going to be from a sample, so it's very similar to when I had a sample mean, but only a sample variance. So what did we do for confidence intervals when I had a sample mean? Looks something like this, where this represented the standard deviation of that sample mean. It's really just notation. Once I have this difference variable created, I've got one sample, right? So it's just going to look different in terms of notation because we want to indicate that my variance and sample mean, right, we're coming from this variable that I created. So it wasn't just from a variable that was measuring something. It was a variable I created based off of two of the other variables in the original data, right? So I can find this mean difference, and it really is just a unique case of the sample mean. I just use different notation to indicate it's from this variable that I had to create, okay? But other than that, it's exactly the same, right? How do we find this t-value? Same way we were before. Our degrees of freedom goes back to being that simple n-1 instead of that crazy complicated, oops, just threw my mouse halfway. It goes back to n-1 instead of that complicated formula that we had to use when we were looking for the difference in sample means. So I know it sounds very similar, right? Difference in sample means is what we were doing before with that Excel male, female BMI. Here, we're going to be looking at the mean of the difference in productivity. So just a little bit different there. Okay. Any questions on that? So I don't say it's a review, but really once we work through a problem, you'll see it's very, very similar to what we did with one population example. So let's say, so I've got this, confidence interval formula. Let's put some numbers to it. So let's say that manager goes through and calculates that the mean difference in productivity was 8.5. The sample size, we had 10 workers. And we had a variance of 121. And at the 95%, if we want to build a 95% confidence interval, what would my alpha value be there? 95% confidence interval alpha is, whatever's outside the interval, 5% in decimal form, so 0.05. Okay. All right. So I had kind of a weird example here where usually we need a sample size over 30. We go all the way back to that central limit theorem. I think in the slides I even said, assume that productivity is normally distributed. That's one way we can get around that central limit theorem. In practice, I'll give you examples where the sample size is over 30 to be a little more realistic. But if we knew that the productivity measure is normally distributed, we can go ahead and kind of work through this example, just like we would any one population sample mean example. Right? So that confidence interval equation looks something like this. Really just a change in notation there from what we're doing with one population. Once I plug my values in though, it's going to look no different, right? How do I find that t-value? Well, I'm going to get this blown up so I can kind of do. We wanted this t-value that gives us alpha total in the tails, or alpha over 2 in each tail. Our alpha was 0.05, so 0.05 over 2. 0.025 was the area we wanted in the tail. What would our degrees of freedom be? Well, it goes back to simply being a one population example, right? Same 10 employees. So n-1 degrees of freedom of 9. I then go to my student t table, add a degrees of freedom of 9. I look up this area I want in the tail, and I'll have that t-value, which is the last thing that I needed. So let's go to that student t table. We wanted 0.025 in our tail here at the degrees of freedom of 9. So 2.262. Now it's just a matter of getting this, subtracting the margin of error to get our lower bound enter in our calculator, add the margin of error to get our upper bound. Okay. Any questions over any of the steps here? Like I said, it's really the same process as what we did with one population means. It's just we got a mean difference, right? This variable that we created. So go back here, get those actual values. Goes from 0.6 to 16.3. So pretty wide range, but still an interesting range, because if I'm going from 0.6 to what, 16.4 about, I'm saying that the true difference, right? Because I had a sample difference, the true difference is somewhere in this range. All these are positive values. So the 95% confidence level, what can I say about the change in productivity from, changing, or what can I say happened to productivity from this change in this workstation layout? The productivity went up, right? I'm doing now minus before, after minus before. So if those are only positive values, it would have to be that the after productivity was on average higher, or that mean difference, that mean change in productivity was positive. On average, worker productivity went up. Okay. So, this is a stupid example about a workstation layout, but you can imagine if I'm changing different things, maybe my compensation scheme, right, for my employees, I could do these kind of, did productivity increase or decrease after this change? Any questions here before we kind of then see how would we do hypothesis testing with this? All right, so with hypothesis testing, it's going to look a little bit different, but it's going to be the same sort of tail, or same three-tailed test, right, left, and two-tailed. So right, left, two-tailed. I'll always use that assumed true difference, just like with the two population examples. I'll always give you that assumed true difference of 0. It's often what we want to know, right? Did productivity go up? Did it go down? Did it just change, right? We don't want to know, did it go up by 5, right? I mean, we can do that, but I'll make it a little bit simpler for us. And also a really common thing we want to do is just know, did it increase, right? So we'll always use that assumed true difference of 0 here. And I'll show you in Excel like what would happen if we didn't, but for our examples, we'll always use 0. Now our test statistic equation, we can actually probably guess what it's going to look like. If we remember what we did for the one population sample mean example, right? We took the statistic we were interested in, subtracted the assumed true value of that statistic. So now our statistic we're interested in is the mean difference. So we'll subtract the assumed true difference, which we said we're always going to use 0 here. And then we'll divide by the square root of the variance on that difference variable over my sample size. So not really a whole lot different here. Just a little bit of difference in notation, because the statistic we're looking at is a little different. It's not just a sample mean, it's the mean of this difference variable we created using 2 other variables. Okay. So go back, right? That's what we're going to have here. Okay. So let's think about this manager example, and let's calculate a test statistic. So it doesn't matter if we want to do a left or right or a two-tailed test here, we would still calculate that test statistic the exact same way, right? If we're going to use that assumed true difference of 0, everything would be exactly the same. All we're doing there is plugging in those values, right? We got this mean difference of 8.5. The assumed true difference we were using was 0. Plug in the variance in the sample size. I mean, this isn't really anything that's wildly different from what we were doing before, right? With just one population mean example. So we found something that was 2.44 standard deviations away from that assumed true difference of 0. We could then look that up in that t-table, find the p-value. My guess is we could probably only put it within a certain range. I said on the exam, I'll give you examples where you could find the exact p-value. We could find the critical values, plot this test statistic against the critical values, see if it's in the rejection region. All the steps of hypothesis testing are going to be exactly what we were doing before. The only difference is this test statistical equation looks a little bit different. Okay. Any questions here? So I think that I jumped to a different example here, and I might save this for Wednesday. I don't think we're probably gonna have time to work through this in class here today, but we'll work through these. I've got a great meme there. But instead, I want to kind of focus on kind of Excel, right? We'll really make this an Excel day, right? So we got an idea about how we do these matched pairs examples. Let's see, oops. X out of that, there we go. Let's see how we would do this in Excel, right? So we've got these matched pairs. Let's see what it looks like in practice. So I'm going to click on this suicide data worksheet. And I had all these different county and as years, and I had male and female suicides in that county in that year. Now I didn't have every county because I think the way that you get the data, I think this is from the CDC. Yeah, it was. I don't think I know. But if counties are too small, we have a little bit of an issue because they're worried that you could identify based off of the characteristics of the person who committed suicide, or you could figure out who that person was. So a lot of the smaller counties you don't have, but I have a really large sample. I have most of the counties in the US. And so I'm thinking about, I've got this difference variable. I'm gonna delete this for a second because I actually created this, right? So usually it's before and after time periods, like that productivity measure, and we're matching the time periods based off the person. Well, here, I'm actually gonna match based off the county, and we're gonna match male and female suicide. So I have these two, these two variables. Before it was productivity before and productivity after. Now it's male and female suicides that I'm matching because I've got the same counties here. So I'm matching on the county. So this is an example where it doesn't have to be time, right? More often than not it is, but it doesn't have to be. So here what I'm going to do is I'm going to take the difference between male and female suicides in this county. I then want to do that for every other county. Well, I don't want to type this in a million times, but I can copy this down. And if I go over to this right corner where I get this big black plus sign, I double left click, it'll copy that formula down all the way to the very last observation. Okay. So I've now got this difference variable created for every county. I'm going to go over here. Now that's what I'm going to use. And I'm going to find my mean difference, which, right, my mean difference, my sample size, and my variance on that difference variable. Those are the three things I needed. Should be able to do that pretty quick, right? The average function, if I can type, the average function, just take the average of that difference variable. That'll give me my mean difference, right? Or if I think about this, I guess I've got D hat, right? Or not D hat. I should call that hat. I should call that D bar. I'm really struggling to type here. All right, D bar there. Okay. I then can find that sample variance using the var.s formula. Select that difference variable. And then sample size, we said we can always use that count variable. And these are the same, should be getting really used to using these functions. Right? So I've got this hypothesized true value of 0. And down here, I think it had a different value, but I'll kind of change it to kind of show you later what if we had a value other than 0. But for now, let's assume we've got this right-tailed test, right? Greater than sign of the alternative hypothesis. So I've got a right-tailed test where that assumed true difference value is 0. So the first thing I'm going to do is go over here. I'm going to calculate some confidence intervals. So if we go back to this confidence interval equation, I now have my mean difference. I have the variance on the difference. I have the sample size. The only thing left I need to do is find that t-value. But we're going to do that the exact same way we did two population examples, with the exception of the degrees of freedom. We now can just use n-1. So I'll use that t.inv function because I know the area that I want in my tails, right? So, or for my confidence interval. So that was just alpha divided by 2. My degrees of freedom goes back to simply being n-1, right? So we were doing before with these matched pair examples. Now, when I copy this down, I want to find the number of standard deviations away I need to go, or this t-value for these different alphas, but my sample size is always going to be the same. So I'm going to go up here and I'm going to freeze that cell reference. Now, when I copy this down, it should give me the t-value I need to build the different confidence levels for the 3 different alpha values. Now, one thing I forgot about is, oh yeah, it's always going to give me the negative value. That's already built into my confidence interval equation, that plus negatives, positive and negative sign. So I'm going to take the absolute value, and then I'm going to copy that down. Okay. So what are my significance levels? Well, significance was really just the percentage of my alpha. So like if alpha is 0.1, that's the 10% significance level. Alpha of 0.05 is the 5%, and then alpha of 0.01 is the 1%. Those would correspond to confidence levels of 90, 95, and 99. Right? So now I want to build my lower and upper bound at these different confidence levels or these different levels of significance. So my lower bound is just going to be take the sample difference, D bar, subtract that T value, the number of standard deviations away I want to go, and then multiply that by, and what this represents is the standard deviation of that sample difference. So that's just the square root of my sample variance divided by my sample size. And I could have calculated this in a separate cell if I had wanted to. With a little bit short of an equation, it probably doesn't save me as much time, right? That would give me the equation for my lower bound. Now, if I want the lower bound at the next 2 levels, I can copy this down, but right, everything's going to stay the same except for the number of standard deviations or that T value. The number of standard deviations I need to go away, sorry, or that T value. So I want this T value cell reference to change, but nothing else. So everything else, I'm going to hit F4 or Command T on a Mac after I select it and freeze those cell references. Okay. Now here, if I hit Enter and copy this down, I've got my 3 lower bounds. Notice with such a high sample size, it's not changing much, right? It's going to be a pretty a pretty tight range of values. Right? Now my upper bound, so the easiest way to find this is if I double click on that cell and just copy, hit Enter to get out of the cell and paste it, should be the exact same value. Doesn't change any of the cell references when I do it that way. The only thing different when I find my upper bound is I'm adding that margin of error. So I change that negative to a positive sign. Now I've got my confidence interval, right, at 3 different levels relatively quickly. Now, if I'm thinking about my hypothesis test, and I've got this assumed true difference of 0, well, the confidence interval is telling me these are like the possible differences or values for the true population difference. 0 is not in any of this range. So we're probably going to be failing to reject the null if I had to guess. I mean, this confidence interval should line up with my rejection decision. So if we go over here, and I want to actually go through and do this hypothesis test. Let me see, where did I have it? Oh, it's down here. There's my test statistic equation, right? So I'm just going to have to use Excel to be my calculator. So take my mean difference, subtract the assumed true difference of 0. Now we don't have to do this if it's 0, but I'm going to change it and kind of show you what it would look like. So that's why I'm selecting that cell reference. And then divide by the square root of my sample variance divided by my sample size here. Okay. So I'm just using it, using Excel to be my calculator for this equation. So my sample evidence was 39 standard deviations away from that assumed true difference of 0. So what is that kind of telling me? Well, if I were to look up my p-value here, my test statistic, oops, well, we'll have to show that later. My test statistic was 39.6. I had a right tail test, so I wanted the area in the right tail. What's my p-value essentially going to be? We said like test statistics of 3 and 4 are pretty large. Yeah, so like the area to the right of 3 and 4 is about 0. So the area to the right of 39, this is going to be almost indistinguishable from 0. In fact, once we do something in Excel, we'll see like this basically is 0. So I've got my test statistic. So I know that t value, I want to find the area in that right tail. So there's a nice kind of, I guess, shortcut we could use, which is there's a RT, a t.dist.rt, that treats this as a right-tailed test. Now, we could just use the regular t.dist. It tells me the area to the left. I would then have to subtract it from 1 to get the area to the right. But if I use this t.dist.rt, it knows it's a right-tailed test. So when you tell it the test statistic, it finds the area to the left, subtracts it from 1, and then gives you that value, right? It treats it like a right-tailed test. So if I just tell it my test statistic, comma, my degrees of freedom, which was my sample size -1, when I hit enter here, it'll give me that p-value. Now, I could also have done 1 minus and just use the regular t.dist, right? So here's my test statistic, comma, here's my degrees of freedom, right? So it'll find the area to the left and then subtract it from 1, and you'll get slightly different values. So the .rt rounds it a little bit differently. Oops, why doesn't it like this? Oh, what else do I need to tell it? Not only my degrees of freedom, but that t.dist, I always have to put comma 1 to tell it make it cumulative, or look at the area to the left. So notice this is a little bit closer to 0, and that's because that .rt rounds the decimal. The regular t.dist keeps it all the way. Like this is so close to 0, it basically is 0, right? But if I use that .rt, it does round it out to that 232nd decimal. But I mean, that's a pretty close enough approximation, right? Out to the 232nd decimal, I think we'd be okay with that. But this p-value, right, e to the negative 232 means move the decimal 232 places to the left. This is a p-value of 0. We could go through and use the if statement to make our rejection decisions, but with a p-value of almost 0, we're easily going to be less than any alpha that we're interested in. So we can reject at every single level here. I think earlier I might have said fail to reject. Sorry, that didn't make any sense. I only would fail to reject the values in the range. So if 0 is not even close to being in the range of our confidence interval. So very clearly we should reject that as a possible true value, which sure enough, we would very easily reject, right? Our p-value is so close to 0, it's going to be less than any alpha. Any questions over anything there? You want to see a cell again, or really only got one more thing that I want to show you here. Now you could work out the whole thing in that completed file. I have like found the critical values, did the if statement, but we've already kind of done that today. I don't want to waste, too much time doing the exact same thing, but you have the completed version of that file as well. It'll be the exact same kind of procedure. But what I do want to show you is, just like with the 2 population example, I can use this t.test built-in formula. Okay. Now it's a little bit different in that my 2 variables, like, well, why can't I just select this difference variable? Remember, I had to create that. So here, I'm going to select male and female suicides. So I'll select the male suicides first, comma. I'll scroll up here so we can see. All right, so put in that cell reference for the male suicide variable, comma. The second thing I selected was the female suicides. So I'll select that column of data, scroll back up so we can see what we're doing. Now notice it's always putting what I'm doing up here in the formula bar, but it's just bigger here, so I know you guys can see it. So that's why I'm scrolling up. Comma, well, what type of tailed test do we have? Well, here we had a right-tailed test, so that's just a one-tailed test. Right? And then comma, we no longer have a 2-sample mean unequal variance example. We're now looking at matched pairs. Remember, we were matching on the county so that we only had really 1 sample. It was all the same counties, they're just different measures, males and female suicides. So here I've got a matched pair example, so it's comma 1, right? That lets Excel know, treat this as a matched pair example. Go through, take these 2 columns of data, create a difference variable, find the mean of that difference, find the sample of that, find the sample size and the sample variance of that difference. Calculate the test statistic using the assumed true difference of 0. Take that test statistic, look it up on the student t-distribution, find the area to the, that's in the tail or more extreme than that test statistic, tell me that p-value. Right. Now, if it was a 2-tailed test, it would take the area of the tail and multiply it by 2, but we told it it was a 1-tailed test here. So hopefully we get the exact same p-value we found before. It's basically the same, right? It's off at the 232nd decimal. Once again, because it's doing all these steps, it does round a little bit differently. So that t.dist keeps the decimal all the way out. The t.dist RT and the t.test do round it, but I mean, they round it out to like the 200 something decimal point. It's basically going to be the same value, right? All these p-values, moving that decimal negative 232 places, that's zero. That's basically zero. So a nice kind of shortcut, once again, that we don't have to do all this work, right? We didn't have to create the difference variable, find all the intermediate steps. It'll just do all of it for us and spit back out as the p-value. Now, that's a pro, and it's a positive of that built-in t.test function. The con is if I ever want to use any other assumed true difference other than zero. So here I found a pretty big difference. On average, the difference in male-female suicides across these counties was 44. That's a pretty big gap. So maybe I'm like, well, yeah, male and female suicides are apparently very different, right? But can I say that difference is greater than, I don't know, 40, right? So I'll change that value of 0 to 40. Notice these update, and actually let's do 42. And the scientific notation here, I'm going to change the formatting because it's just a general number. Because this is really like, oops. Right, there is an actual p-value here. It was just like it was showing us e to the -1. Let's just move the decimal one place, right? So it makes a little more sense to look at it this way. But notice I can change that assumed true difference. And here, yeah, at a 99% level, I can't. But at 90, 95, I can say that the average difference in male and female suicides is greater than 42. Or at least I shouldn't say that it's greater than 42. I can reject that it's less than or equal to 42. And I was really saying kind of the same thing. So I can make some pretty strong statements here using these, hypothesis tests. But the problem is that t.test, it's still the same. It didn't update when I changed that assumed true difference because it can only use the assumed true difference of 0, right? Which is interesting. It's great that I can say that the difference is, greater than 0, that it's positive, that there is a higher male kind of suicide on average, number of male suicides on average than female suicides. But if I don't use that shortcut and I do it all the steps, I can actually say that the difference in male and female suicides is greater than 42, right? Which is a lot, it's saying a lot more than just that they are, that it's higher, right? It's 42 people higher, which, multiply that by the number of counties and that starts to be a pretty large gap in kind of the male-female suicide rate. So I don't know, pretty, important or relevant stuff that we can use this hypothesis testing for. I think on Wednesday, I'll go through those additional matched pairs examples probably pretty quickly, right at the beginning, and then we'll kind of jump into linear regression, okay? So that's the last topic that we'll go through. There's a little bit of hypothesis testing in there, but it's going to look a lot different, and it's going to move from a lot less computation and a lot more interpretation of the statistics that we're looking at when we do linear regression. It's my favorite top part of the class. It's probably because it's like the most useful thing moving outside of this class. So we'll do that on Wednesday, which is what that smart book, I think I called it Learn Smart earlier, Bad Habit, that smart book assignment is going over, kind of prime you for that final topic, okay? All right, so stay warm out there, and then we'll see you guys on Wednesday.